Hola, buenas tardes. Es un gusto para nosotros que nos acompañen el día de hoy al sexto y último seminario del trimestre 23B. Este seminario es una colaboración con el área académica orgánica. Y bueno, como siempre, los invitamos a que se suscriban a nuestras redes sociales, a Facebook, YouTube, en el cual encontrarán información de interés, tanto de divulgación académica y eventos lúdicos que tenemos durante el trimestre. Y bueno, también les recordamos que si están interesados en participar con nosotros como ponentes dentro de nuestros seminarios de cada uno de los trimestres que vamos a tener más adelante, se pueden comunicar con nosotros al correo uam@izt.uam.mx. Además, en el departamento contamos con otros medios de divulgación, los cuales tenemos una gaceta y un podcast. Para mayor información, ustedes pueden ingresar a nuestra página de química.iz.uam.mx o bien comunicarse directamente con los organizadores, el doctor Ricardo Peralta Ávila, la doctora Lucero González Sebastián, en el caso del podcast y en el caso de la Gaceta con el doctor Humberto Laguna y el doctor José Luis. Y bueno, el día de hoy tenemos un invitado muy especial que viene desde Francia. Nos acompaña con el tema Asymmetric synthase of functionalized cyclopropanes with a fluorinated group CF3, CHF2, CH2F. Primero me voy a permitir leerles una pequeña semblanza del doctor. El profesor Philippe realizó sus estudios de doctorado en química con especialidad en química orgánica y con mención honorífica en la Universidad de Rouen, con la tesis titulada Generación electroquímica de carboniones alfa fosforados, alfa halogenados, electrosíntesis de dihalógeno alquenos y ciclo alquifosfanatos, demostración de un fenómeno de activación electroquímico de magnesio. Realizó estancias postdoctorales en el Laboratorio de Tecnologías Electroquímicas y Electrotecnologías de Hydro-Quebec, Centro de Investigación de Shawinigan, Quebec, Canadá, con una beca de excelencia Hydro-Quebec. Y en el laboratorio del profesor Agarwal en la Universidad de Sheffield, Gran Bretaña, con la beca europea Marie Curie. Fue profesor en el INSA de Rouen e investigador en el equipo de profesor Quirion y posteriormente profesor titular de INSA. Actualmente es profesor en la Universidad de Rouen en el laboratorio COBRA, Química Orgánica, Bioorgánica, Reactividad y Análisis, y director del Departamento de Química Fina e Ingeniería del INSA de Rouen desde junio de 2009. Ha dirigido más de 30 tesis, 25 defendidas y 7 en progreso. Supervisor de 35 becarios postdoctorales, cuenta con más de 123 publicaciones y 5 patentes. Welcome, Professor Philippe, y go ahead, please.
Thank you very much for this kind introduction. It's my pleasure to be here today and try to share with you some of our recent results regarding the catalytic and non-selective synthesis of cyclopropane. So, okay, why cyclopropane? Propane is a quite popular scaffold in medicinal chemistry. And as you can see here, cyclopropane is the 10 most counter cycle and the sub-carbo cycle after benzene and cyclohexane in the drugs approved by the FDA. It's an ester of alkyl group. It generally leads to conformation reversing scaffold, and in general, you can expect to have an improved metabolic stability. So on this slide, you can see several examples of bioactive cyclopropane, and one main feature of this cyclopropane is that in many cases you have functional groups such as, for example, imidazole, amine, amide, and as you can see here, you have silaprizan, cypromine, minalcipran, and trigagalor, BMS, and UPS. And as you can see, these cyclopropane are quite functionalized, and so it's quite interesting to be able to synthesize efficiently, asymmetrically, if possible, this type of cyclopropane. The second, next please. So the second topic I would like to talk with you is the importance of fluorine in medicinal chemistry. So fluorine is very popular in medicinal chemistry and in agrochemical. About 40% of agrochemicals have within their structure at least one fluorine atom, and about 20 to 20% of in medicinal chemistry. So it's because fluorine has atypical properties because of its high electronegativity. The CF bonds are important unique character. This is a short bond with a high stability, and the van der Waals radius of this atom is between hydrogen and oxygen. That's why, for example, CF2 scaffold is used as a mimic of oxygen. So when you introduce a fluorine atom onto a molecule, there is some consequences because of these properties. In particular, you can observe a modulation of the pKa value of the adjacent function and modification of the lipophilicity, some conformational effect called Gauche effect, enhanced metabolic stability because of the CF bond strength, and some influence on the bioavailability. Next, please. So there is many examples in the literature of fluorine compound with very important bioactive activity. The historical one is a fludrocortisone developed by Fried in 1953. You can see a Prozac with a CF3 group, some the Lipitor, with this, which is used to prevent cardiovascular disease. Very famous compound, vinfluenine, developed in France by Pierre Fabre Laboratory. And this CF2 moiety in vinfluenine has been incorporated in a very atypical manner using superacidic condition, SBF5 and HF. You have also acetylimide with a 2-fluorine in para position of the aryl group. An important contribution from Professor Blackburn from the University of Sheffield. It was demonstrated that this difluoro phosphonic acid is a mimic of a natural phosphate, and more recently, nirvatrelvir is used for the treatment of COVID-19. And to demonstrate the efficiency of fluorine chemistry, about 80 fluorine-containing drugs approved by the FDA was reported between 2010 and 2019. Next one, please. So the combination of fluorine atom and cyclopropane could lead to very interesting scaffold, in particular with bioactive properties. And I show you here some examples, such as this antagonist of metabotropic glutamatergic receptor developed in Japan by Taisho, a fluoroanalog of valproic acid, which is used for the treatment of epilepsy, citalopram, one inhibitor of histone. And as you can see, in many cases on the cyclopropane bearing the fluorine, there are also some functional group. One famous compound, the vacilaprevir, which is an HCV inhibitor with 2 different CF2 difluorinated group, a CF2H and this CF2, and 2,3 cyclopropane. Next one, please. And finally, I want to show you perhaps a counter example of the interest of fluorine chemistry. In collaboration with Janssen, this compound without the fluorine is Asymmetric, an HCV inhibitor, which is marketed by Janssen. And through a collaboration with Janssen, we have decided to develop the total synthesis of this fluoroanalog. And as you can see on this slide, the bioactivity of the fluorosimipravir is very low, about 15 micromolar. Micro is missing here. And the explanation is that with the fluorine, there is a complete change of conformation of the cyclopropane, leading to a loss of interaction with a specific amino acid of the protein. So in this slide, next one, please. I summarize most of the strategy developed to make cyclopropane. There is 3 main strategies. The first one in either Simon-Swiss cyclopronation, so between an alkene and this diodomethane. Generally, it's come through zinc carbenoids, and in most cases, the R group is the H. The second way to make cyclopropane is Michael-induced ring closure, MIC reaction. So you can have 2 different types. One, for example, from sulfur halide, and the one for addition on the Michael acceptor. and intramolecular cyclization to deliver the expected cyclopropane. The second approach is to have the leaving group on the Michael acceptor, and in that case, you have almost the same strategy as intramolecular cyclization to deliver the cyclopropane. One of the most popular way to make cyclopropane is to use diazocampan. So you treat this diazocampan with a series of metals such as rhodium, ruthenium, copper, or cobalt, generate metal carbene and addition. Generally, the general mechanism admitted for this transition metal catalyzed cyclonate comes from the formation of the carbene, extrusion of nitrogen to deliver the metal carbene, and then the asynchronous concerted mechanism to deliver the expected cyclopropane. There is also other approach, such as chemistry or Kulinkovich reaction, but specifically to access cyclopropane. So now I would like to show you the main strategy to access cyclopropane with one fluorine atom or one fluorinated group. So regarding the synthesis of fluorocyclopropane, you can use diazo compound, such as on the right, aryl diazo compound, or more simple monoacceptor diazo compound in a combination with alpha fluorostyrene and with a rhodium catalyst. And as you can see, Professor Hofer in Germany developed quite efficient catalytic and endoselect synthesis to access this type of cyclopropane. Another strategy is to start from these alpha fluorochiral sulfonamines, one for addition on the 1,1 amides, the first deprotonation, one for addition, cyclization to deliver the expected cyclopropane. But in that case, when R2 is a methyl, for example, he observed a very decrease of the enantioselective level. A last approach is to use this allylic alcohol in combination with diethyl zinc, and this catalyst deoxyborolane in the presence of difluoromethylbutomethane. During this step, it was developed by Professor Charette in Canada. During this approach, there is a halogen scrambling, explaining why he got the monofluorinated cyclopropane. But in that case, it's important to note that it's need to use one equivalent of the chiral catalysts. Regarding the access to fluoromethyl cyclopropane, I report here one example from this monomethyl fluorostyrene and this diazo compound using a gold catalysis and this spiral catalyst, and the author obtained quite a good result in terms of yield, DR, and EP. And regarding the access to difluoromethyl cyclopropane until 2017, there is no example in the literature. Finally, for the trifluoromethyl cyclopropane, this is the most studied series of fluorinated cyclopropane. As you can see, there are many examples, but most of them are used the same strategy. That is to say, the CH3 moiety is on the diazo compound, and you use mainly styrene derivatives. You can use rhodium catalysis, iron catalysis, cobalt catalysis, or more recently, the group of Fazan from the University of Rochester developed a biocatalytic approach using this diazo CH3 compound and the styrene. And more recently, some other group developed an original strategy, but in most cases, the alkene partner is a styrene. And finally, in 2022, Marek and Kara developed the functionalization of trifluoromethyl cyclopropene to deliver this trifluoromethyl cyclopropane. In our case, we are quite interested to combine different types of diazo compound, for example, donor acceptor diazo compound, di-acceptor diazo compound, and mono-acceptor diazo compound in combination with a series of fluorinated alkene, such as alpha CF3, alpha CF2H styrene, or acrylate bearing a fluorine atom, or allylic species bearing in position 2 a fluorine or another halogen. So first, I would like to show you our result regarding the catalytic and non-selective synthesis of difluoromethyl cyclopropane. For that, we combine the use of this nitrodiazoketone, so PMP for paramethoxyphenyl, in the presence of this alpha CF2H styrene in DCM and minus 20 degree, 1 hour addition, and in presence of this rhodium BTPCP catalyst to deliver the expected cyclopropane in very good yield, excellent DR, and very good EE. So we spent a lot of time to identify the right catalyst, and finally this rhodium BTPCP was identified as a magic catalyst in our case. And this rhodium 2 catalyst was not so popular in cyclopropane. It was initially proposed by Professor Davis in the US. And this rhodium BTPCP is very easy to synthesize. You combine this donor-acceptor diazo compound, this styrene, rhodium dust, then saponification of the ester moiety, ligand exchange, and you can synthesize very efficiently this rhodium catalyst. As you can see on this slide, this is only a selected example. We can modify the aryl moiety on the styrene, bearing a methyl in para position, diabutyl, methoxy, chlorine. For this, the last one, we were able to get X-ray analysis or benzoxazole series. In all cases, we obtain very good yield, excellent DR, and very good EE. It's also possible to modify the diazo compound. For example, you can use this thiazoketone and this keto-diazo ester. In both cases, we're able to obtain the expected cyclopropane, but in a moderate EE 70 in the first case and excellent EE in the second case. It's possible to extend the reaction to aryl diazoacetate. We absolutely use the same reaction condition, and as you can see, in many cases, we obtain very good yield between 77 and 90. Excellent DR in most cases, except in the case of naphthalene, for which we have an erosion of the DR, but in most cases, the EE is almost very, very good. It's possible also to modify the aryl moiety, but when we install a nitro in para position, we observe an excellent EE, but the reactivity and the yield was very low. Regarding the thiophene, we observe a very good yield, excellent DR, and moderate EE. It's also possible to modify the aryl moiety of the diazo compound, bearing, for example, a bromine, nitro, thiophene, and in most cases we obtain almost the same. We obtain the same results. We next examine the possibility to extend the cyclopronation to alpha-3 styrene. So for that, we have to modify slightly the temperature to -20 and to get the expected cyclopropane. But in that case, it was not possible to use the nitrodiazoketone. We have to use the cyanodiazo esters. In that case, we can obtain very good yield, excellent DR, and excellent EE. We have 9 examples of alpha-3 styrene. It's also possible to extend the reaction to other types of alkene, such as, for example, the alpha-bromo CF3 alkene, or this acrylate bearing a TS3 input, an alpha-TF3 acrylate. In both cases, we obtain moderate yield, moderate EE, and we actually work to improve these results. It's also possible to modify the aryl moiety and to use aryl diazoacetate, except instead of the use of diazo compound, and again, we obtain very good yield and EE. Finally, we extend the reaction to monohalogenomethyl styrene, and for the fluorine series, we have again to decrease the temperature to -50 to obtain excellent reactivity, DR, and EE. And for the 2 other halogen, fluorine and bromine, we have to increase the temperature to -20 to get the same type of results. The next question was, is it possible to combine this donor-acceptor diazo compound and this alpha-fluoroacrylate? Normally, fluoroacrylate and electrodeficient alkane are not compatible a priori, because of the electrophilicity of the rhodium carbene. So normally this carbene reacts with electron-rich alkene, but in 2013, U. Davis showed that it's possible to combine this donor-acceptor diazo compound and this acrylate or acrylamide with its rhodium TCP-AD, and he obtained quite interesting results in terms of yield, TR, and EE. But when he used an alpha substituted acrylate, such as in this example with the CH3, he obtained moderate yield and a quite important erosion of the EE. So we decided to examine the possibility to combine this donor-acceptor diazo compound and this alpha-fluorobenzylic acrylate. For that, we screen quite a large number of rhodium catalysts. We decided first to examine the reaction at 40 degrees, and the addition time of diazo compound was 2 hours. But as you can see with these three first rhodium catalysts, the DR are quite low and the E are very, very low. And finally, Amandine Ponce, PhD student, identified rhodium TCP-TTL as a quite efficient rhodium catalyst. We obtained above 95 to 5 DR, promising EE on the major diastereoisomer. So she spent a lot of time to optimize again this reaction, and finally she found that if we carried out the reaction at -20, and if we had the diazo compound over a period of 8 hours, we were able to obtain the expected cyclopropane in very good yield, about 64%, an excellent DR, and a very good EE. We are able to modify the aryl moiety by iodine, bromine, chlorine, fluorine, and in most cases of CH3 group or chlorine in metaposition. And as you can see in many groups, except for this one, the chlorine in metaposition, for which we have an erosion of the EE, we obtain quite similar results. Generally, the isolated yield of this compound are quite low because they are quite difficult to isolate in a pure form. It's also possible to modify the acrylate moiety. So we use, for example, this alpha-fluoroamide, this 2,4-allelic species bearing phthalimide, a chlorine, a bromine. What is interesting in that reaction, if you can see that if you use chlorine or bromine, the DR is generally excellent, but in the case of fluorine, the DR is almost a 1-to-1 ratio. So we have now modeled to explain this difference. It's because we are competing in the case of fluorine, it's because we are competition between two different transition states, whereas in the case of chlorine and bromine, one transition state is really favored. And finally, we can use this 2-chloro-allelic sulfone, and again, we get very good ER and excellent EE. So the next question was, is it possible to try to combine this alpha-fluorobenzyl acrylate with another type of diazo compound, more challenging, that is to say this dia-acceptor compound? Up to date, there is no example in the literature using rhodium catalysis in an intermolecular manner, but there is a very important work by Zhang Group in the US who was able to carry out the cyclonation of this acrylamide, acrylonitrile acrylate with different type of diazo compound, nitro-diazoester, thieno-diazoester, or even this keto-diazoester in a very efficient manner using this cobalt porphyrin catalyst. There is one example, an intramolecular version between this thieno-diazoester and this acrylate developed by Professor Charette, but as you can see, the yield is very low and the E is good, but not excellent. So this work has been done by Jonathan Decamp, a PhD student, and Alej Becher, postdoc, who is now a young assistant professor in our institute. So they combine this alpha-fluorobenzyl acrylate and these thieno-diazoesters. So as you can see in this table, they spent a lot of time to optimize this reaction. And as you can see, for example, if you use rhodium E base, you have absolutely no reaction. The same observation is for rhodium TCP-TTL. And finally, if you use again rhodium BTPCP in dichloromethane at -20 degrees, you can obtain a quite interesting yield, about 50%. An interesting DR, about 80 to 20, and a promising E, 82. So we try to optimize again this reaction, and finally they identify specific condition, a quite complicated reaction condition. We have to use first 3 equivalents of diazo compound added over 8 hours, and then we had 1 additional equivalent of diazo compound during 4 hours. This reaction occurs at -35 degrees, and this time we're able to obtain 85% isolated yield, a very good DR, 80 to 20, and an excellent EE, 93. So we have now here about 21 examples, so I'll show you only some examples, but as you can see, we can have this, you can modify the ester, benzyl ester or methyl ester. You observe only a slight erosion of the EE, 92 to 88. We can use alpha vinyl fluorovinyl sulfone, fluorovinyl phosphonate. We can modify also the diazo compound from this cyano-diazoamide of this cyano-diazoketone. In most cases, the EE remains very high. In some cases, the yield are quite low, about 40%. We are able to obtain X-ray analysis for this alpha-butyl acrylate, 82%, and excellent EE on each diester isomer. It's also possible to check the alkene. As you can see, we can use simple benzyl acrylate, simple vinyl sulfone of this alpha-methyl benzyl acrylate or alpha-related benzyl acrylate. And in most cases, the yield excess is quite good, except for this one, and the EE is quite interesting. And finally, we also be able to obtain this fully functionalized cyclopropane 3R, for which it's quite important to know that these 2 functions are a direct precursor of amino acid function. So we are working actually on the use of this type of cyclopropane for medicinal application. So here, as you can see, there is 2 types of rhodium BTPCP, the S1 and the R1. The S1 you should have to synthesize it, and the R1 is now commercially available. So in red you have the result with the R enantiomer. Another very interesting result is that if you use this electron deficient allene, this benzyl alenoate, we are able to obtain quite interesting result, about 56% yield, and a quite interesting DR about 80. But in our strategy, there is some reluctant substrate, such as, for example, this vinyl phosphonate or this other alkene. There are also some reluctant diazo compound, for example, the CF3 diazo ester or this cyano-diazophosphonate or this nitro-diazoketone. So we can also do some quite simple functional group manipulation, such as, for example, the deprotection of the terbidyl ester or the reduction of the nitrile and the protection of the primary amine. We can also do the saponification of the benzyl ester and then the peptide coupling reaction with glycinate in a quite efficient manner. And we have now enhanced some other functional group manipulation. So this is a quite versatile approach to cyclopropane. So regarding this result, the result I showed you a few minutes ago regarding the cyclonation of electron deficient allene, if you look at the literature, there is not so many examples, and up to our knowledge, there is only 1 report in the literature. I showed you in a few seconds, but the main report concerns the cyclopropination of allene. So this is, for example, using rhodium DOS or rhodium E base, or more recently, in 2014, Professor Iwasa in Japan used ruthenium catalysis and especially ruthenium phiox to obtain quite efficient cyclopropanation of alene. Up to our knowledge, the only report in the literature is this one, reported by Charette in 2013. It treated this thiazole ester and this benzyl alenoate with rhodium E base. You obtain a very low yield, a poor DR, and the E is not reported in the paper. It's probably because this E was not measured or very low. So we decided to examine the cyclopropanation of electron-deficient alene. That has been by two postdocs, Yoko Asigawa, who has started as an independent carrier in Japan, and Thomas Quentin. So we examined two types of diazo compound, so donor-acceptor diazo compound, either with a methyl group, methyl ester, or terbutyl group. And we identified that the use of rhodium TCP-AD in dichloromethane at minus 15 degrees deliver the expected cyclopane in a very efficient manner. The isolated yield is 91%, an excellent DR, and a very good ER. So we examine the scope of the reaction, and as you can see, we can modify again the group present of the aryl moiety of the diazo compound. So with the bromine, fluorine, iodine of CF3, we obtain almost the same result, excellent DR, excellent yield, and almost the same ER. It's possible to install also a methyl group in para position. We observe only a slight decrease of the EE, and they are remain quite good. We can install also a terbutyl, a methyl in meta position of two chlorine atoms in meta and para position. And again, as you can see, we obtain almost the same result with a very good yield, excellent DR, and quite good enantiomeric ratio. We have also some reluctant substrate of this donor acceptor diazo compound bearing in para position, a methoxy group, or a methyl group in ortho position, or electron returning group in para position. And it's also possible to extend the reaction to other type of electron deficient alene, such as this alpha-methyl alenoate, of this alene bearing a sulfone group or phosphonate group. And as you can see, in most cases, except for the alpha substitute alenoate, for which we have to use 2.5 mol% of catalyst instead of 1.2 for all the other substrates, we obtain a quite good yield, excellent DR, and excellent EE. It's also possible to change the nature of the donor of the di-acceptor diazo compound. For example, you can install a Weinberg amide, a phosphonate, a cyanide group. And in most cases, as you can see here, we obtain quite moderate yield, essentially because this compound is quite difficult to isolate in a pure form. But the ER remain quite good for example, the thiazole ketone and this benzyl alenoate. But in other case, we observe some erosion of the ER. So we are working actually to try to improve that series, which has delivered some quite disappointing results. So the next goal was to try to combine allelic species bearing in position to either an halogen group or a methyl group or an aryl group in combination with a di-acceptor diazo compound and donor-acceptor diazo compound. So in the literature, there is some example that we have shown, but this is quite limited example, and we want to expand the scope of this type of reaction. So for that, we imagine to use this allelic sulfone or this allelic trifluone or this allelic silane and combine them with two types of diazo compound, di-acceptor and donor-acceptor diazo compound. For that, we use again we identify that the rhodium S-PTPCP, so this enantiomer or the other one when we use the commercially available, as you can see, we are able to carry out this combination between this donor acceptor diazo compound and this alpha 2-arrelated allelic sulfone in a quite efficient manner, 93% yield, excellent DR, and excellent EE. So as you can see, we can, I show you only a selected example. We have now here about 25 examples. Again, it's possible to modify the structure of the donor acceptor diazo compound, essentially on the arene moiety, using, for example, a chlorine in paraposition, nitro in paraposition, a thiophene, methyl group, and in most cases, the yield remains quite excellent, the DR is excellent, and the EE is quite good from 85 to about 94% EE. When we use less electron-rich allelic species, by studying, for example, this nitro group in paraposition, we observe a good ER and excellent EE, but in this time, we obtain only 27%. But with using a fluorine, we could recover high reactivity, high DR, and excellent EE. We next examine the possibility to use different type of allelic species. And as you can see on this slide, using allelic sulfone bearing an halogen in position 2 or a methyl group in position 2, we identify that we have to carry out the cyclopropanation at -20, and in most cases we obtain quite reasonable yield, excellent DR, and quite very good EE. When we modify the function present on the allelic position, for example, the SO2 CF3 or silane, we have to modify the temperature and decrease it to -50 to have a very good conversion of the starting material. And as you can see, with an alpha-related allelic species bearing this SO2 CF3 or silane, we can obtain the expected cyclopropane in quite good yield, moderate or good DR to excellent DR, and the EE remains excellent. Regarding the use of quite simple allelic silane, we observe an erosion of the yield and a very important erosion of the EE as well when we use this type of allelic species bearing a bromine in 2 positions and an ester in 2 positions. So we are working on this type of allelic species to try to improve our results. It's also possible. Next, we plan to apply this cyclonation of 2-arrelated allelic sulfone to diacceptor diazo compound. So for that, we use the same reaction, and as you can see, we obtain reasonable conversion. But the isolated yield was quite low, and the DR and the EE was very modest. In particular, the EE for the major diazo isomer was 5%. So Ling, a PhD student, spent a lot of time to try to optimize this condition. And so she tried to modify the structure of the diazo compound with, for example, this diazo keto diazo ester, keto nitro diazo ester, or this nitro diazo ester, but we were unable to obtain any traces of cyclopropane. She tried then to modify the structure of the allelic sulfone. In most cases, we observe very low DR and modest to quite interesting EE, but not so very good. And finally, she found an atypical result. So with this allelic sulfone bearing in position 2 an ester moiety, and in that case, she obtained a very good result, about 90% isolated yield, quite good DR, 80 to 20, and excellent EE on both diazo isomers. So we decided to examine the scope of this reaction, and by installing in position 2 either a phenyl group, you see we have very bad result in terms of EE. When we install an ester group or a keto group, as you can see, we obtain quite good yield, moderate DR, but for the majority, we obtain very good EE. And what is very interesting is that if you change the nature of the diazo compound, coming from this cyanodecyl carbutyl ester to this CF3 diazo ester, again we obtain good yield, excellent DR, and quite good to excellent EE. What is interesting to note is that this type of cyclopropane bearing a CH3 and an ester is not so common in the literature. Up to our knowledge, there is this example of the use of this diazo compound in asymmetric cyclonation. It was developed by Professor Muller in 2004, but there is only 5 examples, and the EE are between 12 and 55, and the radium catalyst used in that series was radium DOS. So we are working on this new catalytic and not just selective cyclonation of this diazo compound, and we plan to develop this type of cyclonation. So finally, I would like to show you our result dealing with the use of the most simple diazo compound, monoacceptor diazo compound, ethyl diazoacetate. And this diazo compound is a quite popular diazo compound in catalytic and non-selective cyclonation. So as you can see, there is some quite conventional approach to the cyclonation of this type of compound, reported by Bruno, by Scott, Zhang, Iwaza. You can use copper, ruthenium, iron, cobalt, and quite interesting result has been done by Professor Arnold and Fazan using myoglobin or BM3H star, and they are able to quite efficiently carry out the biocatalytic cyclopropane of this ethyl diazoacetate. And next one, please. So we decided to examine the combination of this ethyl diazoacetate and 2 substituted allylic derivatives. The most important contribution has been reported by Professor Iwaza in 2021 using this diazo ester and this allylic silane. You obtain quite good DR, quite modest to very good DR, and excellent EE for each example, between 92 and 99% here. So we decided to examine the combination of this diazo ester and that series of allylic species with a substituent in position 2. So initially, we try a model reaction between this diazo ester and this 2-fluoro allylic ether with a paramethoxy transit group, and to optimize and to maximize the obtention of the cyclopropane, we decided to use 5 equivalent of the alkene and 1 equivalent of the diazo compound. So the reaction was carried out at -10. 4 hour addition, and then 1 hour at room temperature. So as you can see, we test a different type of approach. So a classical copper with a bis-oxazoline ligand, but we obtain absolutely no conversion. We can also try to use rhodium BTPCP, which has delivered quite efficiently many cyclopropane during our study. But in that case, we obtained very low conversion. And finally, we decided to examine ruthenium catalysis, and especially we use the ruthenium phiox. And with this ruthenium phiox, we obtained quite interesting conversion, about 40%, but the EE on each diastereoisomer remained very quick. So we decided to optimize this reaction using this ruthenium catalysis. So for that, and because of the price of this fluoroalkene, it's this 2-fluoro allyl ether is synthesized from the 2-fluoro 3-fluoropropane, and it's a quite expensive starting material. So we decided to change the stoichiometry. So we use 1 equivalent of the alkene and 3 or 5 equivalent of the diazo compound. And by modifying the temperature and the rate of addition of the diazo compound, we are able to obtain full conversion of the starting material. And we obtain a mixture of 1-to-1 diastereoisomer. And for each diastereoisomers, we are able to obtain a very good EE, 93 for the trans one and 86 for the cis one. What is interesting to note is that for many cyclopropanes obtained in that series, we can very easily separate the 2 diastereoisomers. So we examine the scope of the reaction, and as you can see, the DR on the majority of this example remain modest. The best one was about 80 to 85 to 50, but in all cases, we obtained quite good yield, except with this 2-fluoroallyl-sulfone. But the EE remained excellent on both diastereoisomers, and these 2 diastereoisomers are very easily to separate, except for the last example with the benzyl ester and a bromine in alpha position. For this one, we obtained good yield, but the mixture was the mixture of diastereomers was not possible to separate these diastereomers, and the EE remained quite interesting. It's also possible to modify the aryl port, the allylic species, sorry, with a sulfone, with a methoxine paraposition, chlorine, also with a very simple sulfone, allylic sulfone, being a methyl group in position 2. And again, we obtain excellent yields, moderate DR, and excellent EE on each diastereoisomers. And finally, it's also possible to extend the scope of the reaction from this 2-arylated allylic triflone, silane. We can use also a very simple silane or an allylic silane with a methyl group in 2 positions. We can also scale up the reaction to 2 millimole scale, and we can confirm that our cyclopronation is quite robust on 2 millimole scale. But we have also some reluctant allylic derivative, such as this allylic phosphonate, allylic amine, phthalimide, or this allylic sulfone bearing in position 2 a ketone. Finally, we examine, I show you here only one example of post-functionalization. So we use this starting material, 80% EE. We carried out the reduction of the ester to the primary alcohol, protection of the alcohol, elimination reaction to deliver this methylene cyclopropane. And these methylene cyclopropane are quite popular scaffold for medicinal application. We are trying actually to remove the sulfone group, but it's quite difficult. We have not very good results because we have, in many cases, a ring opening of the cyclopropane. So in conclusion, I would like to show you what we have done during the last 6 years. So we have hand now a library of cyclopropane bearing either a CF2H, a CF3, a CHF2, or more simply a fluorinated. We can also carry out the cyclopronation of electrodeficient allyne or allylic species, allylic sulfone. We have also some results regarding the use of this CF3 diazo ester. And quite recently, we have through a collaboration with Professor Fazan in the US, carried out the cyclopronation using biocatalysis between ethyl diazoacetate and alpha substituted styrene bearing a CF3 group, a CF2H. And quite recently, we use this chiral cyclopropane. We modify the ester with in a fashion to obtain an activating group, and we carry out the CH bond activation on the last carbon available on the cyclopropane to be able to synthesize this tetrasubstituted cyclopropane in a quite efficient manner. Actually, we're working on different topics, the incorporation of some of this functionalized cyclopane in more complex structures through collaboration with peptide chemists, for example, or biologists. We are using also collaboration. We are using a computational chemistry to try to fully explain the energy selectivity and the direct selectivity observed in all these series. We are also working on the design of new chiral catalysts for actually unsolved asymmetric cyclonation using rhodium, for example, rhodium catalysis, such as nitrodiazoester or diazomalonate. And actually, we're working on this in collaboration with specialists in machine learning for the design of new and accessible catalytic energy cyclonation. So finally, I would like to thank first the ECOS program for giving me the opportunity to present you our results. All the students who have been involved, who are still involving in this different project. I would like to thank Professor André Charette from the University of Montreal for our fruitful collaboration. Professor Claude Legault from the University of Sherbrooke for the computational approach. Professor Fazan for the collaboration using biocatalysis. All the institutions for financial support. This industry, Janssen, Novalix, and Auril Industry, who are actually supporting directly or indirectly our research. All my collaborators in the foreign team, Thomas Poisson, Tatiana Besset, Samuel Bonner, Jean-Philippe Bouillon, and Thomas Casanero. And finally, I would like to thank you for your kind attention.
Thank you, Professor. An interesting topic, difficult for me. Question, please?
Hello. Okay, very nice talk. And I was very curious about your magic catalyst, which you mentioned like about a third of the talk, right? It was this ruthenium catalyst. So for what I could work out, you were working under homogeneous conditions, is that right? Have you tried anything related to heterogeneous, like? Would you like to? Okay, let's talk. Cheers, mate.
There is some example, for example, from Iwasa's try to do some catalysis,
you know, it's because I reckon that it's a completely different environment when you try it. And since what we do is about materials, right? And we demonstrated how to incorporate ruthenium in a very particular way. So the distances between those two rutheniums, a long story, but I need to show you the crystal structure. And but I reckon that not just in terms of the yield conversion, but what we've seen when it's defined in an environment where everything is confined, that the kind of catalysis and the kind of products that you obtain are completely different. So that's what I'm very curious to see in real world, like, because this is the thing, like their reactions that you try, and they're really interesting and that they have a real purpose. So we materials people, we just try a simple reaction just to prove the concept, but we are like, what if we try this material in the real world? So the kind of work that you do. So let's talk about a beer. All right, cheers.
Thank you very much, Professor. I think Professor Illich was speaking of MOPs. So I think he's speaking of MOPs, but also we have MOPs of ruthenium that you can incorporate rhodium within a MOP, and then you can use it as a catalyst. So I think another approach is to use rhodium as a catalyst and then to perform your reactions. Also, the other question that I have is, you perform the reactions at really low temperatures. Is that because the diazo compound that you use? Or why did you use that temperature? Like almost in all the reactions, it was -20.
When you try to do a cyclonation, when you try to do a cyclonation, we have two competitive reactions: the cyclonation of the alkene and the homocoupling of the diazo compound to give not the dimer, but the homologated compound. So this is a competition between cyclopronation and homocoupling. So in some cases, you have to decrease the temperature to -50, or yes, -50, and then you have to increase it to -20. So it's really depending on the alkene partner. So you have to test it. You have to test it.
Thank you very much.
Again, thank you very much for your nice talk. I wonder if you have some ideas about the mechanistic cycle of this process.
Of cyclonation?
Yes.
Yes. The first step is the formation of the metal carbene with the release of the nitrogen, and this is the limiting step of the cyclonation. So if you have to use nucleophilic diazo compound to have an efficient formation of the metal carbene. And then when you have this metal carbene, you have a 2+1 cycloaddition. And generally the mechanism is an asynchronous concerted mechanism.
Thank you very much.
Thank you for your talk. Respect biocatalysis of cyclopropanation. You use myoglobin, but
Not
can excuse me.
Not me,
Yeah,
Professor Fadan.
okay.
Yes. I never
Okay,
use
okay.
myoglobin.
Okay,
Okay.
but can hemoglobin catalyze the reaction?
I think yes.
Okay.
Yeah.
Thank you.
¿Alguien más?
Thank you very much. I wonder if you know what are the reasons why fluorinated molecules are better inhibitors. Does anybody have described the kind of interactions it established with the protein? What kind of is like a hydrogen bond donor, excuse me, acceptor, or what kind of interaction does it establish with the
Regarding the
protein?
hydrogen bond donor, it's a long debate with the community. Yeah, I think there is evidence on the crystalline structure. You can see some interaction, but here, in many cases, it's to protect some position towards, for example, metabolic oxidation. That's the main reason. That's the main reason of the popularity of fluorine chemistry. There is some new emerging fluorinated groups, such as, for example, CF3, which is considered as a super CF3, but there is no so many in vitro or in vitro study for this compound.
Thanks, Philippe, for your very nice talk, especially that you prepare a different kind of compounds with a special group, in this case, the fluor. And I have a question about the functionalization of the ester group. In your slide 36, you have a reduction to alcohol. Maybe you can stop it in the aldehyde, because
Yes.
the aldehyde is another group very good for any chemist. Did you try it to?
No, we haven't. My PhD student didn't try it because generally you have to control the reduction, and he preferred to reduce totally to the alcohol.
Okay.
Yes.
Just for
But I
protecting.
think if we take care, we can easily get the alcohol.
Yeah, because with the aldehyde, you can incorporate this
Yeah.
kind of molecules in another.
Yeah.
In another.
Yeah, sure.
Thank you.
Thank you, Professor. We have shared a certificate with you. One moment, please. Eduardo, ¿gustaría decir algunas palabras para el doctor antes de finalizar? En lo que compartimos. Ya, gracias. No, bueno.
En français. Bon, merci Philippe pour ta conf. On est vraiment content que tu es là. Donc, elle était très jolie, on l'a beaucoup apprécié. Le sujet, je pense qu'on aura de petites collaborations entre les gens d'ici et ton labo. C'est la première fois. Je pense qu'il faut remercier Ecos Nord aussi et l'Université de Rouen à Normandie. Merci.
Bueno, certifiqué. El Departamento de Química de UAM Iztapalapa otorga la siguiente constancia al profesor Philippe Jubault por el seminario dentro del ciclo de seminarios del Departamento 23P. Sorry. With the topic Asymmetric synthesis of functionalized cyclopropanes with a fluorinated groups F, CF3, CH2, CH2F on October 2, 2023. Firman el doctor Jorge Gaza, Chair of the Chemistry Department, and Reina Ojeda López, coordinador. Thank you for your presentation. Thank you. Y a todos, bueno, los que nos acompañaron hoy de forma virtual, de forma presencial, les agradecemos mucho su presencia. Les deseamos que pasen un buen intertrimestral y nos vemos el próximo trimestre. Gracias a todos.